Section 13.3 is about arc length and curvature, and we're going to start by talking about arc length. I'm going to just start with an example. If I suppose that r of t is a position function, so giving an object's position as a function of time, so that then I know that r prime of t would be its velocity, and the magnitude of r prime of t is the speed of that object. Well, I know from single variable calculus that as a general rule, if I integrate from a to b velocity, and I'm purposely writing that out because this holds whether I'm dealing with velocity as a real valued function or a vector valued function. What I will get is displacement. For a real valued function, displacement would be a signed number, and for a vector function, it would be a vector, which would indicate the direction that I've come from my starting point to where I am now, and the magnitude of that would be the distance from where I am now to my starting point. It's also the case that if I integrate speed with respect to time, for a real valued function, that's the absolute value of velocity. For a vector function, that's the magnitude of the velocity. What I will get is the distance that I have traveled. Now, with a position function, if this is my position at time A, and I travel along, and this is my position at time B, the distance that I've traveled is simply going to correspond to the length of the path that I've traveled along. So that would correspond to the arc length of this particular curve. Okay, so if I integrate from a to b the magnitude of r prime of t dt, if that's a position function, that's going to give me the distance that I've traveled. But we can generalize this to any old curve. It doesn't necessarily have to represent a particle's position. If I integrate the magnitude of the derivative, I'm going to get the arc length. If my function represented position, that arc length corresponds to the distance that I've traveled. If it represents something else, we're just talking about arc length. So this is S, which is arc length. S is generally the symbol that's used for arc length. Okay, I'm sure there's a reason for that. You'll notice there are no S's in the word arc length, but I'm sure that in some other language, quite possibly Latin, there's a word for arc length that has an S in it. Anyway, there's a reason for it. I'm just not sure what it is. Okay, so we sort of can see why that makes sense from looking at this particular example, but this is true in general for any curve, provided that the derivative is continuous. So the function needs to be continuously differentiable, the derivative needs to be continuous. So let's just make that caveat, if r prime of t is continuous. So I can calculate arc length for any curve that's parametrized so that it is continuously differentiable. Let's just do an example of that. Let's let r of t be cosine t, natural log of cosine t, sine t, where t varies from 0 to pi over 4. I modeled this off one of the even numbered problems in the book, although I don't think it's exactly the same. Okay, and I want to try to find the arc length of this over this interval. Okay, well, r prime of t would be negative sine t, 1 over cosine t, chain rule, times the derivative of cosine, so times a negative sine t, and then cosine of t. You'll notice on this interval, cosine is going to be in between 1 at 0 and root 2 over 2 at pi over 4, so it's totally fine, first of all, that we're plugging it into the natural log because it's positive, and then that it never shows up in the denominator. Okay, now notice this is just negative sine t, negative tan t, cosine t. So if I look at the magnitude of r prime of t, that's going to be the square root of sine squared t plus tangent squared t plus cosine squared t. Now, Pythagorean identity tells me that sine squared plus cosine squared is 1, so that becomes the square root of tangent squared t plus 1. Now that's awfully nice because I've got another Pythagorean identity that tells me that that's the square root of secant squared t. That is not secant t. That is the absolute value of secant t, because secant is sometimes positive and sometimes negative. To know which it is, I need to look at what t values I'm plugging in. If I'm plugging in t values between 0 and pi over 4, t would correspond to an angle in quadrant 1 where everything is positive. So I can drop that absolute value, but only because I know that t is between 0 and pi over 4. And remember, I do need to see this work, because if you don't write it, I can't tell the difference between a student who just assumed that the square root of secant squared is always secant of t and a student who thought through this process. So you do need to document that thought process. Okay, that's very nice. So now I can say that S, my arc length, is just going to be the integral from 0 to pi over 4 of the magnitude of r prime of t dt, but that's just the integral from 0 to pi over 4 of secant of t dt. Now I left a lot of space here. That's because I remember the trick for integrating secant. And the trick is to multiply by a clever form of 1. I'm going to multiply by 1 in the form of secant t plus tan t over itself. What that does is now we've got the integral from 0 to pi over 4. On top of my fraction, I've got secant squared plus secant t times tan t. And on bottom, I've got secant t plus tan t. And if I do a u substitution, let's let u equal the bottom. I could, if I wanted to, write out secant plus tangent. I'm just going to call that the bottom. Then u prime is the top, because the derivative of secant is secant times tangent, and the derivative of tangent is secant squared. Okay. So du is just the top dt. And so this becomes the integral from, let's see, my u value at 0 would be secant of 0, which is 1, plus tangent of 0, which is 0. 1 plus 0 gives me 1. 2, my u value at pi over 4 is going to be secant of pi over 4 plus tangent of pi over 4. Okay. Secant of pi over 4, that's the reciprocal of cosine of pi over 4. And tangent of pi over 4 is just 1. Okay. So, let's see. That's going to be cosine of pi over 4 is root 2 over 2, but it's also just 1 over root 2. Okay. So, if I take the reciprocal of root 2, I'm going to get root 2. Okay, so we're going to 1 plus root 2. Okay. And then this becomes, we're integrating 1 over u du. So that's just going to be the natural log of the absolute value of u evaluated between 1 plus root 2 and 1. So that's the natural log of the absolute value of 1 plus root 2 minus the natural log of the absolute value of 1. Now, when you've got numbers inside of absolute values, I believe that you can see that that is a positive number, and I'm okay with you dropping the absolute value, which you should do to simplify it, to be just the natural log of 1 plus root 2. We always do want to evaluate the absolute value. If it's a number, you don't need to tell me, oh, it was positive, so I did this, okay? But if it's a variable, you need to tell me why it was positive or negative, and so that you simplified it the way you did. This is just the natural log of 1, which is 0, and so we get the natural log of 1 plus root 2 is our lovely arc length. Okay, so you will find that when you're working with arc length, because you're integrating the magnitude of the derivative, and that always involves a square root of some squares, there's sometimes a little bit of interesting work involved in the integration. Okay. Now, some of that showed up in this particular example. I'm not going to go through every possible quirk that can show up in the integration. Really important in this section that you are doing the homework, because that's going to force you to review some of your integration techniques from previous semesters. My rule for exams is I'm testing you on 3C. I'm not trying to test you on 3B. So I'm not going to look for an advanced integration technique from 3B and just throw it at you as a surprise. But I do expect you to know the techniques from 3B. So if a technique from 3B has shown up in class or in the homework, I would consider it fair game on an exam. But I'm not going to suddenly throw you an integration by partial fractions or a trig substitution if we haven't seen it either working together in class or it hasn't shown up in the homework. But if you don't do the homework, it's entirely possible that you're going to be weaker in your integration skills than you should be. Okay, so I will try to write fair exams, assuming that people have watched these lecture videos and done the homework.